and by which we are going to check the relative stability of your system. We are going to see what is the root locus, what is the angle and magnitude condition, and how to make the root locus, and few examples. Okay, so this is actually mathematical based topic, as we all know that your control system is more or less towards mathematical approach, having the mathematical approach. Let's start it from here. Let's see what is actually root locus. Here you can see this system. Can you see this? This is a feedback system with unity feedback, right? And the transfer function of this system is this one is GS is equals to K by S plus 1. Okay, so this is your gain of the system. Your feedback is unity minus 1. So what will be the open loop transfer function is nothing but GS into HS, and this is your GS, which is K upon S plus 1, and HS is 1. So your open loop transfer function will be nothing but this: GS is equals to K over S plus 1, because your feedback is nothing but 1. Okay, and what will be the closed loop transfer function of the system? Here you can find out the closed loop transfer function: GS upon 1 plus GS HS, and HS is 1. So your closed loop transfer function will become GS over 1 plus GS, and this will be K over S plus 1 plus K. Is okay, good. So now here, if I'll ask you to find out whether the given transfer function, this one, is stable or not by Raut-Hurwitz array, what you will do? You will take the denominator and you will make the Raut-Hurwitz array, right? And you will find out whether there is any sign change in the first column or not. But here the thing is, this K, it is a variable. This is again K and variable, and you don't know the value of K. So in that case, if the value of K changes, your pole values also will get changed, because pole will be what? Roots of the denominator. This is your denominator, S plus 1 plus K, and if your K is changing, your pole will also get changed. Okay, so now here you can see, let's say I'm taking the different values of K. Let's assume first K is your 0.5. So in that case, your pole will be S plus 1 plus 0.5. So S will be equals to minus 1.5. Okay, and minus 1.5 is here, this one. Let's say K1 now, and if we are having gain value 1, K equals to 1, so your pole will be equals to S is equals to
minus 2.
Minus 2. So this is your minus 2, and as we progress or further keep on increasing the value of K, let's say 5, so what will be the value of pole? That will be minus 6, somewhere here, right? Minus 6, and let's say at 15 your value will be minus 16. So this is the yellow color pole is showing over here. This is minus 16, right? So what we are saying over here, as you are increasing the value of K, your poles are going this side, more deeper side of negative plane, and as you are decreasing the value of K, we are decreasing the value of K, your pole is going towards this, or you can say it is going towards the axis. Let's assume that this is your imaginary axis like this. So now is it clear that how the value of only the position of the poles, how it can be altered by just increasing or decreasing the value of gain K. So now is it okay that how your gain K can dictate the pole locations? And also we have seen that if we are increasing the value of K, your poles are getting much deeper side of S plane, negative side. And if we are decreasing the value of K, your poles are going towards the imaginary axis. And once if your poles are getting crossed imaginary axis and getting entered in the positive or right hand side of the plane, what happens?
It becomes
Your system will get unstable, right? Your system will get unstable, right? This is the main problem. Now this is simply your first order system, because the power of S is 1 over here in the denominator.
1.
So this is first order system, and by taking the different values of K over here, we can first make the table, and then we can see the different position of the poles, and by that we can say that all the values of K, my system is stable. Okay, because if I'll just
finding this value by putting S1 1 plus K is equal to 0.
of course I'm just finding the roots of this denominator. and roots of the denominator is nothing but the poles.
Pole.
Okay.
Okay, so for the first order system, it is pretty much simple to check the location of the poles by or with different values of k. But as we increase the order of the system, let's say your order of the system is getting third order or fourth order, there you have the four poles for that particular system. Because first order system you'll have only one pole, second order system you'll have two pole,
Two poles.
and for third order system you'll have
Three poles.
so as you're increasing the order of the system, this approach is not going to help you to find out the location of the poles with respect to different value of k. Now you're getting the point. What is
Yes,
the
sir, yes.
difficulty over here? What we are going to discuss? Again, I'm repeating. If your order of the system is first order, second order, or you can say your order of the system is less, or it is not that much high order up to the second order, so you can see the for the first order system will have only one pole, for the second order system will have two poles, and you can easily find out the value of those poles with different values of k, and then you can plot on your S plane, and then you can see whether your poles are getting crossed imaginary axis and getting entered in the positive half or not. So there on you can say for all the values of k, your system is stable. Like for this particular system, if k is 0, if your gain k is 0, your transfer function will be 0. Okay,
Yes, sir.
because 0 divided by something will be 0. Now let's say minimum value of k is, let's say I'm assuming 0.01. So in that case 0.01, what will be the value of pole will be 1.01. So the minimum value which you are going to have for the pole is which will be greater than minus 1. So minimum value of pole will be greater than minus 1, because anything k which is greater than 0 will give you the pole location greater than minus 1. Okay, so this system is going to be stable for all the values of k. This system is not going to unstable for any value of k. So this is what we are going to see.
Sir, if
What we are
given
going
sir
to
k
see.
is greater than 0.
So what we are going to check? We are going to check if your gain k, if it is from 0 to infinite, what will be the value of poles? So I'm going to increase the k from 0 to up to the infinite, and I'm going to check my pole locations. For any value of k between 0 to infinite, if my poles are crossing imaginary axis and going to the right hand side of this plane, so I can say up to that value of k my system is stable, and beyond that value of k my system will become unstable. Root locus is nothing but it is a method which gives us a kind of a graph, or you can say locus of the poles, and poles are nothing but the roots of the denominator or roots of the characteristic equation in the S plane as we vary gain k from 0 to infinite. You got it? What is the definition of root locus? Because it is not feasible for us to make a table for higher order system as we are increasing the value of k and check the values of the poles and then plot those poles on the S plane. That is not feasible. It will become very tedious. So we need some method where we can have the locus of the poles, that how my poles are traveling in S plane as I'm increasing the value of k from 0 to infinite. If all the poles of the system are traveling in only in the left hand side of the S plane, I will say my system is stable for all the values of k. If for any particular value of k, any pole of the system is getting entered in the positive, or let's say right hand side of the S plane, so my system will become unstable. So root locus will give us the locus of my poles, or how my poles are traveling in S plane. That is the root locus, nothing else, as I'm increasing the gain k from 0 to infinite. Like here, this is your, let's assume that this is your closed loop transfer function, any closed loop transfer function, just for an example, this one. And what is the order of the system? It is fourth order, right? 2, 3 and 4. So the order of the system is 4. So how many poles will have? We'll have 4 poles. So now let's assume, right? Now let's take the similar approach, the approach which we have taken for the first order system. Now let's say k is 0.5. Can you give me the values of the poles? all the 4 poles. So it is difficult. Of course, multiple values होंगी. You will have 4 poles.
4 values आएगी, 4 values आएगी.
You will have the 4 values. So it is become difficult or will become tedious to find out the poles with different values of k. And here we have taken only point, but we have to approach up to the infinite value. So that approach is not going to help us out. Okay.
So but we will get
4 values.
So now here,
What we
we have just
from the
derived from the, take an example.
Okay, so this will become tedious if we have order of the system higher than 3. That's why we need root locus, and this method is given by Evans, and this method gives the locus of the roots of the characteristic equation plotted on S-plane, and this is going to be plot on simple graph paper, and even you can also plot in on simple your A4 size sheet. So and now I'm going to start with your method, root locus method. There are 2 main conditions, or you can say the based condition, angle and magnitude criteria related with the root locus. Let's assume that this is your system where you have gain or your open loop transfer function GS with feedback transfer function HS, and your closed loop transfer function will become GS over 1 plus GS into HS. Okay. So now here your characteristic equation, which is nothing but the denominator of the transfer function, is 1 plus
1
GS
plus
HS
GS
equals to 0, and SHS will be equals to minus 1 from this equation. And remember, the multiplication GS HS is a complex quantity. Okay, so I'm going to break this term into 2 parts. One is the magnitude, other one is the angle. If you can remember the polar form of the complex numbers, we have 2 forms, rectangular and polar, and in the polar we have magnitude with some angle.
the angle.
Right. So the same thing I'm going to do for this given equation. So the angle of GSHS minus 1 will be the angle of GSHS, the complex term, and angle of minus 1. So this will become A at an angle of theta. That is nothing but, if it is minus 1, if it is coming out minus 1, that means what? Plus minus 180 degree. This suggests if your angle is this much, 180, and 2k plus 1, k is not gain over here, it is some arbitrary value. You can take it A, B, C, D, anything, because if I'm taking k from 0, 1, 2, 3, 4 up to, so this will give me only the odd numbers. If it is 0, 1, if it is 1, it will be 3, if it is 2, it will be 5. So 180, 180 into 3, 180 into 5, 180 into 7. So this is your angle criteria. So if your angle is coming out, angle value is coming out minus 1, so your theta value should be of this order, plus minus 180 and 2k plus 1. You should not worry about this. When you will use this angle criteria, then you will see that what is the meaning of the angle criteria. And the other one is the magnitude. The same characteristic equation I am taking over here. SHS is equals to minus 1. And the magnitude is, I have taken the mode out of here and equals to the mode of minus 1. So it is nothing but the magnitude of GSHS is nothing but 1. Okay, this one is simple. The root locus is nothing but locus of the poles as we are increasing the gain k from 0 to infinite. So let's assume that this is your second order open loop transfer function over here. Third order open loop transfer function k over s into s plus 1 into s plus 2 with unity feedback. So this is your open loop transfer function, GSHS. This is your open loop transfer function. And what will be the closed loop transfer function? 1 upon GS, 1 upon 1 plus GSHS. Okay. So you can find out the closed loop transfer function. What I'm showing you over here, that your root locus, when your gain k is 0, when your gain k is 0, is always starts with open loop poles. Okay, poles when your k is 0 for the closed loop transfer
0
function.
minus 1,
Because characteristic equation will be what? 1
0 minus
plus
1 minus 2.
right. So characteristic equation will be 1 plus GSHS, right? And this is GSHS is given to us, and 1 plus GSHS will be what? S into S plus 1 S into S plus 2 plus K. That will be your characteristic equation. And if your k is 0, your poles value will be 0, -1 and -2. 0
Yes.
and these poles values are nothing but equals to the open loop poles. This is your open loop transfer function and the poles values are 0, -1 and -2. So this gives an idea that your root locus will always start with open loop poles. Again, remember what we are going to check. We are going to see that how your poles are traveling, closed loop poles are traveling in S plane as I'm going to increase the value of k from 0 to infinite. And when your k is 0, the closed loop poles values are equals to your open loop poles. When your k is 0, your closed loop poles values are equals to the open loop poles. So it suggests that your root locus will always starts with open loop poles. Now let's see. I have the location of open loop poles over here. 0, -1 and -2. And I have just taken some point. This wrote a red dot over here. Any point anywhere on the S-plane. But here, just for example, I have taken this point over here and I want to check whether this point will be a part of the root locus for the given transfer function. Okay, I just want to see whether this point will be a part of root locus for the given transfer function. Or let's say I'm taking one more point over here, red dot. So I would just want to check. Let's say I am having the root locus like this. The red one I'm just plotting, just some kind of root locus I'm plotting. I'm just giving you an idea. Let's say your poles are having this kind of locus, like they have started from here, open loop poles, 0, -1 and -2. This -2 poles is going in the deeper side of the S plane as you are increasing the gain k. So this is going this side. These two poles, this pole is going towards the left, this pole is going towards the right. They have met somewhere here, then they have breaked out, and one pole is going like this, the other pole is traveling or having the locus like this. So this is a kind of a, I have just given you an example. It is not the root locus for the taken example, just to give an idea. So here you have three poles, and how many loci you have? Three locis, because we want to check how each pole travels in S plane as we increase the value of gain.
Okay.
So now you understood what we are going to check, how we are going to check. So you will have three loci related with each pole. So this pole is going towards left. These two poles are converging towards each other. They met at some point and then they have break away. And then one pole is going like this. The other pole is going like this as I'm increasing the value of k from 0 to infinite. So from this example, I can see that this pole is always going towards the negative. So this is not crossing your imaginary line or getting entered in the right hand side of the S plane. Whereas these two poles, as I'm increasing the gain k, this value and somewhere at this. Let's assume at this point your k
Sir,
value is, let's assume, yes,
समझ नहीं आ रहा.
we have taken an example where we are having three poles, third order system. Is it okay? We have taken third order system. Okay, and for the
Yes,
third
sir.
order system, we'll have three poles.
Three poles.
Now, what we have to check all these three poles, how they are going to travel as I'll increase the value of k
Okay.
from 0 to infinite. This is my motive.
Infinite.
I have to check whether any pole is crossing the imaginary line and getting entered in the this positive half of the
Right
display
side.
or right hand side of the display. If any pole is getting entered in the positive half, then your system will
It will become
become
unstable.
right. So here I have just given you an example that, let's say this is your root locus. This pole is going towards left, and these two poles are having this kind of a root locus. And here, where they are getting the imaginary axis, the value of gain k is 100. So if you're having this kind of a root locus for any given example, guess what? Up to the value of k 100, your system is stable. As you are
Stable.
increasing the value of k greater than or more than 100, your system will become
It will become
unstable because your two poles are getting entered in the positive half of the S-plane or right hand side of the S-plane. This is just an example. Okay, this we need to check through root locus method. And how I have plotted this root locus, this is we are going to study that how we need to plot the root locus for any given example. The root locus which we have plotted just right now, I have taken one example. Okay, this is not we have dealt till now. We have to see that how we need to plot the root locus for any given example. And how many loci will have for any given example?
ऑर्डर पे डिपेंड करेगा.
Exactly, उसके order पे depend करेगा. Let's say if it is third order system, you will have three poles, so you'll have the three loci. If it is a fourth order system, you will have the four poles and you will have the four locus of each pole. That's how each pole is traveling in S plane as I'm increasing gain k from 0 to infinite. Now, is it okay? Is it clear that what we are going to check from the root locus? So before that, I have taken, let's say this point again, P2. Okay, and I want to check whether this point is a part of any loci, because we'll have three loci, this pole, one for this pole, and other one for this pole. So will this be a part of any loci? Okay, how we are going to plot the loci? Let's say this is your pole, and I just need to plot the loci for this pole, increasing the value of gain k, and I'm taking the values of the poles. Just for an example, one value is here, and then finally I'm joining all the values. That's how we plot generally, but that is not feasible as we have seen as we increase the order of the system. So now let's say if I want to check any arbitrary point on the S-plane, whether that is a part of the root locus or not, is done by the angle criteria. We have just now seen the two criteria, angle criteria and magnitude criteria. If the any point on S plane satisfies the angle criteria, then it is a part of that root locus for the given system. I'm repeating again, we have just now seen the two criteria. One is the angle criteria, other one is the magnitude criteria. Not only this point, let's say I'll take one point over here. If this point satisfies the angle criteria, then this point is definitely a part of the root locus. That means any one of the pole will travel through like this and will have this point on its own loci. That is what I'm talking about here. Okay, let's say also part of the root locus is satisfy the angle criteria. That means any three of the loci, any one of the loci from out of three poles will have this point as its own locus. So let's check the angle criteria for this one. The angle criteria, how we are going to check this angle criteria? I'll draw the phasor from each pole, from 0 this one, from minus this one, and from minus to this one. From 0 pole, what is the angle made to this point? It is 180 degree. And this pole, what is the angle made by this pole at this point? It is 0 degree. And what is the angle made by this pole at this point? Again, it is nothing but 0 degree. So this pole makes an angle of 180 degree to this point. This pole makes an angle of 0 degree to this point, and this pole makes an angle of 0 degree to this point. Now let's sum up all these three angles. So one is 180 degree, angle made by minus pole minus 1 location, and minus 2 is 0 degree. So angle minus 1, angle made by 0 pole at minus 1 and minus 2, this is how we are going to check the angle criteria. Sum up all the poles negative. So this is minus 180 degree, minus 0, and minus 0 is equals to minus 180 degree. Okay, and what was the angle criteria? GSHS, angle made by GSHS should be equals to plus minus 180 2k plus 1. So this is satisfying your angle criteria because your angle is minus 180 degree here. This one plus minus 180 2k plus 1. Here is not starting from 1, it starts from 0. This is printed over here. K can be started from 0, 1, 2, 3. So all the angles made by this point is coming out minus 180 degree. So that means it satisfies the angle criteria, and that shows or concludes that this point is definitely is going to be a part of root locus. Now let's take one more point. I have taken this point over here. I just want to check whether this will be a part of root locus or not. So I'll draw the phasor to this pole, from this pole, from this pole also. And what is the angle made by pole, open loop pole at 0? It is 180 degree. What is the angle made by minus? Again 180 degree.
0.
No, 0. Why 0? And what will be the value of angle made by pole minus 2? Again
180 degrees.
180. So sum all these three angles. Minus 180 is coming out minus 180 into 3, right? And again it is satisfying the angle criteria, which is plus minus 180 into 2k plus 1. When k is equals to 1, it gives you the 180 into 3. So this point also satisfies the your angle criteria. So this point will also be a part of your root locus. Okay, so guys, let's conclude the session. Today's session we are going to now we are going to check the. Okay, let's take this point over here. I have taken this point over here, and I want to check whether this will be part of root locus or not. Okay, so what I'll do, I'll draw the phasor from this pole up to that point. I'll draw the phasor from this pole to that point, and I'll draw the phasor to this point. And now let's check the angle. This is 0 degree, this is also 0 degree, and this one is also 0 degree. All the three open loop poles makes an angle of 0 degree to this point. Okay, and if you sum up all the three angles, it is coming out 0 degree. And your angle criteria is, it is
180 degree.
180
plus 1 plus minus
2. Okay,
minus 1.
so this point
Plus
is
1.
not satisfying the angle criteria because it is coming out 0 degree. This is not going to be part of the root. तो कोई भी तीनों में से कोई भी एक पोल आपका इस पॉइंट से नहीं निकलेगा. दैट इज द मीनिंग. अगर समेशन सेटिस्फाई कर रहा है इस क्राइटेरिया को, तो वो पॉइंट आपका रूट लोकस का पॉइंट होगा. उसका मतलब ये है कि कोई भी तीनों में से एक पोल उस पॉइंट से होकर गुजरेगा. And I want to check whether this will be part of any loci out of these three loci. So how I am going to check this? So for that purpose, I have an angle criteria. Till now, we have seen what is the significance of angle criteria. If any point on S plane satisfies the angle criteria, that means your locus or any loci will
pass through the.
Quickly conclude the session. We have started with the relative stability because absolute stability is not going to serve the purpose for all the parameter values or variations with respect to time. So that's why we need to see the relative stability of the system. For that purpose, we have taken out the root locus method, and root locus method gives us the locus of the characteristic roots of the characteristic equation, which is nothing but the poles of the system. So root locus gives us the locus of the poles, that how your poles are going to travel in S plane as I'm going to increase my gain k from 0 to infinite. And for that purpose, I have, or we have seen the two criteria, angle criteria and
magnitude criteria.
And if any point on S plane satisfies the angle criteria, that means that point is going to be a part of that root locus for the particular system. So till now we have seen this. Now in the next session we'll see that how to plot the root locus. Till just we have seen the significance of the root locus and what kind of information you can realized or derived from the root locus. Mainly it is nothing but the stability. We just want to see that any pole, any value of k is should not cross the image line and should not get connected in the positive path. That
right side
information we want to get from the root. Okay. And if we have, let's say, if we have a plot in our hand, given an example, we can easily tell that for that whether the system is going to stable or not for all the values of that is the purpose of the locus.